Given a system of equations, we're asked to use a matrix method to find x and y in terms of a and b. So I've got a matrix that I'm timesing x, y by, and then I'm going to get 1, 3. And because it's a squared x, I'm going to put a squared here. That'll give me my a squared x when I multiply it out, and then a minus 2 here, and that will equal the 1. Okay, so I'm writing it as a matrix equation instead of these simultaneous equations as shown. And then there'll be a 1 here to get me x, and plus b squared. Okay, and then I will call this A, and I want to find the inverse. Now you might remember in for 2 by 2 matrices what the inverse is, like write it straight down. I think if I thought about it hard, I probably could, but I'm just going to use the kind of the general form, and we'll go from there. It's just one less thing to remember then, and it doesn't take too long. So it's going to be 1 over the determinant multiplied by the transpose of the cofactor matrix. And then we just got to work out the determinant. Do that first. So it's going to be a squared b squared when I times along this diagonal minus 2. So it's going to be a squared b squared plus 2. On to the cofactor matrix. So this is when you pick each element. We're in the first row, first column here, and you basically cross it out and you take whatever is left. The determinant of technically if it was a 3 by 3, but here I just get b squared. I'm trying to work out why I wrote plus b squared there. Sorry, I didn't actually mean to. Okay, so I'm going to get b squared up here. The only extra thing you need to think about is whether we use plus or minuses, and the rule is that it's going to be plus, minus, minus, plus. It's always minus 1 to the power of the row plus the column. For this one, it's probably easiest to just go with that. So the next one, when I pick I'm going to pick this one here, I'm going to cross it out, and I'm going to get 1, but this time it's going to become minus 1. Keep going. If I pick this one, I'm going to get minus 2, but then I'll make the negative of that, so it'll become 2. And then finally, pick the b squared one, cross it all out, I'm going to get a squared, and it's going to be positive because it's minus 1 to the power of 2 plus 2. That's my cofactor matrix. The transpose then just means that I swap these around. Like if it's the second row, first column, it becomes the first row, second column. So b squared and a squared stay exactly where they are. But this is of course, we haven't proven this, but you can prove it. It's quite a nice little exercise to do. I know it seems very technical, but once you get into the groove of it, you know, if this is not making sense, you just got to go back and practice 2 by 2 matrix inverses. Because I don't want to go back to the very beginning. I'm just applying the formula, and now I'm ready. Really, the inverse is going to be 1 over a squared b squared plus 2 multiplied by b squared 2 minus 1 a squared. Okay, and therefore xy, what we do is we multiply on the left both sides by the inverse, which cancels this one out. It's essentially the identity. So I get 1 over a squared b squared plus 2 multiplied by b squared 2 minus 1 a squared, and that is what I'm going to multiply 1, 3 by. And I've got my solution. So x is going to be, well, I'll deal with the 1 over in a minute. I'm going to get b squared plus 6, and I'm going to divide that all by a squared b squared plus 2. That's my solution. And y is then going to be minus 1 plus 3a squared, or 3a squared minus 1. Again, I need to divide that by the determinant. And that is our matrix method. It's given us a solution in terms of a and b for the above equation. Finally, we're asked to explain why the method used in part A works for all values of A and B. So the determinant of A, the only time that it fails is when it's equal to 0. Then it's called a singular matrix. You can't have an inverse, so you can't solve the equation. But here we've got the determinant, remember, was a squared b squared plus 2. And this is ab squared plus 2. So it's going to be greater, remember a and b are real, it's going to be greater or equal to 2, so it's definitely greater than 0. So that's a always positive, therefore inverse always exists, and there will, I'm using the word always a lot, I'm going to use it one more time, always be a solution.